please.
Austin Thompson.
Yes, sir.
Go ahead.
Thank you very much.
This is you.
Yeah.
Isaac. Jake. Come on, Dad. Hunter. Chandler. He's not here.
How you doing?
I don't think. Sang. He sang. And you see him?
I thought I saw him earlier today, but I don't know.
Well, he's probably time late. Anyway, I put the solutions up. Did you look?
Chandler.
We can go through it if you want. It's a pretty straightforward problem. The only thing,
If you don't mix up signs, it's a lot easier for me. I said you don't mix up signs, it turns out a lot better normally. But yeah.
all right, let me, I'll go. I almost feel like trying this because it's elevated right now. But I learned my lesson about this. We're going to do circulate really 3 port, 4 port, and Wilkinson's the riders will be the last topic. And I mean, if you want, I can do microwave amplifier design. That's a little bit beyond what we usually do, but I don't know. Is anybody interested in radar or microwave? Microwave is what radar is, or any kind of anything with radar communications, Wi-Fi, all the stuff with the Internet of Everything. Well, I want to tell you one thing. The big deal is always getting the signal amplified and then received and more or less decrypted. It's really, they use the word demodulation. Nowadays, it's more decryption algorithms because things they're sent and they use encryption algorithms nowadays. So it becomes a much more complicated deal to undo them. Normally, when you deal with Ethernet cable and everything like that, and fiber optic, you don't even look at the pathway. You just look at the signal after it's decoded or demodulated. But the real truth is, in the real world, when people, the Wi-Fi guys I know over here, and they look at what's called the physical layer, and that means what they're looking at is the raw signal as it's sent and received, and everything from there. Because ultimately, from that point on is really where a signal can be intercepted and then it can be modified. Things can happen to it. So I'm not going to get into microwave engineering too much, but I'll tell you that microwave amplifier design, things like that are very important. And I'll just say one last thing before I get into this 3-port business and 4-port. The reason we talk about 3-port and 4-port is because they're very useful when you transmit and receive information. Especially, have you heard the term MIMO or MIMO? Multiple input, multiple output is the standard way transmissions are done. What it means is, if I have a radar or a telecommunication system or even Ethernet, I won't send out one signal. I'll send out 10. And I'll receive, or I'm sending 10 out there, and other people receive 10. Some are time delayed, other things like that. And that requires multi-ports to operate and do certain things. That's the reason we use this. Now with radar, it's pretty simple because it's usually line of sight with straight pass. and you'll have many antennas that are all going in and out of the same port systems. Now, all right, so that's, I hope I said this right. With radar, you send something and then something bounces back. The way that information gets sent comes from a power amplifier, and you have to have some way when it's received, if it uses the same antenna, that it's actually routed to a different point, not the power amplifier, and that's where these things come in. So here we go. This is going to be 3-port systems. By the way, before I start, does anybody have a question about the homework I did? Y'all got it then? I'm afraid to ask sometimes because I don't know if you did it or not. If you did it, do you have questions? Jacob, I'm happy. I'm used to getting at least one question for every homework assignment on average. I think it was that way for quite a while. And it's good because that tells me at least somebody's looking at this stuff and they have a question. All right, so for 3-port systems, typically it boils down to this. We talk about circulators. That's the primary one. We also talk about something called the Wilkinson's divider. So the first type of 3-port system is a circulator. And the second is a Wilkinson's divider. By the way, this one was made in about 1960 by a guy named Wilkinson. Clever design, by the way. It's cheap and it's lossless. So anyway, when we talk about 3-port systems, I back up even before I get to circulators. I'm just going to show you a typical 3-port splitter. You're used to the term splitter, right? This is not very hard to see. So this is a quote splitter. And it's a 3-port system. Here's what it amounts to. You want a really cheap way of taking a signal and dividing it into 2 paths and making sure there's no reflection. Follow me on that? That's the idea. So what's the cheapest way to do it? And wideband for that matter? Well, it's using resistors. Downside of using resistors is you have power loss. Remember that. So when you go to Radio Shack, it used to be Radio Shack, and I guess when you go to Best Buy or you go online and you buy splitters, it'll take like the coax cable and route it to 2 coax cables. The idea is they want no reflections at these ports. That's the idea. So what do? They do this. Remember, you're going to have a transmission line here coming in, characteristic impedance Z0. Then you're going to have transmission lines Z0, transmission lines Z0. The idea is if a signal comes in this way, no reflection, and it's routed the other way. But you're going to lose power. So the way they typically do it is this. They'll have something where there'll be a resistor R here, and I'm going to put down the value in a second. Then another resistor R here, and another resistor R here. I hope you follow me. And I'm trying to show you how these things are transmission lines. So they're going to come together. It'll be like that, but here's your router. These are transmission lines with characteristic impedance. Here's your router. Y'all follow me? Now, this is the idea of zero reflection coefficient. If this is port 1, call this port 2, call this port 3. We want the input impedance right here, or Zin, to be equal to Z0. Y'all agree if Zin looking this way is equal to Z0? It's impedance matched. Y'all see that? Right? I mean, if you're looking, cut that thing. If this is a coax cable, think of it that way. And you're looking and you see the characteristic impedance, your coax, nothing's reflected, right? So what do we do with these resistances? Now think about it for a second and hear me talk this stuff. All right, look right here. From this point this way, I have R plus Z0, don't I? As the characteristic impedance. It's in parallel with this point, which is R plus Z0. Y'all follow me? but it's in series with this, which is R. You agree with me? So here's what I'm going to do. I'm going to say Zn on port 1 would be equal to R. By the way, this is a good way to reason through these things for any number of ports. As long as there's nothing complicated, you can always put things in parallel very easy. And if they're symmetric. So this is going to be R plus, and then it's the parallel combination. Now look, it's R plus Z naught, but there's two of them, so it'd be divided by 2, wouldn't it? So it's going to be R plus Z naught divided by 2. Now make sure you agree with me. Y'all see it? All right. So we got to solve for R, and we want Zn actually to be equal to Z naught, don't we, for impedance matching? So I just replace Zn with Z naught. Y'all see this? Everybody with me? All right, so what is R? Well, if I look at this, I have Z naught is equal to, and this is going to be 3/2 R, right? 3/2 R plus Z naught over 2. Do y'all agree? I'm just going through the motions of making sure you do. I want to solve for R, so I'm going to subtract Z naught over 2 from both sides. Do you agree? And y'all see here that therefore R would be Z naught over 3. And in your book, if you look on page 570, he'll show you the value for R that'll make this splitter work is Z naught over 3. Do y'all see it? You can put that, it's page 570. Just look for a second. But notice the reasoning process. I didn't do this in a pack. This is a wide band matching network. Now, I'm going to get the port parameters, but you all see that this will work. There's no reflection. That's the idea. You never want reflection. It's the number one thing when you have any of these things, 3-port, 4-port, 5, 0 reflection. Because the minute you get reflection, you get a huge amount of power loss. And you also ask for trouble because when you reflect energy back into a power amplifier, you're going to destroy things at times. So that's the goal of all these things: splitters, circulators, couplers of any type. You want a reflection coefficient about 0. Now this is wideband; it's not a function of frequency. But the downside is you have 3 resistive elements that are going to burn up power, and therefore your scattering, this is a lossless matrix, your scattering parameters will not be, frankly, they're not going to be just ones or zeros. They're going to have 1/2, something like that. So to get the scattering parameters, we can go through it, but if you assume a voltage here, I'm just going to tell you how it's done. I'll give it to you, V naught, right? Then you can say, well, V naught is there. And if I look at this, I'm going to just put it right here. This is port 1, and I'm going to put plus or minus V naught. Here it's coming in. This is R was Z naught over 3, right? Now, at this point, I'm going to look at port 2, but you'll notice that these two networks are in parallel. I have R plus Z naught, R plus Z naught. Y'all follow me? I want the value at Z naught, don't I? So because they're in parallel, I can put R over 2 plus Z naught over 2 as a replacement for those circuits. Remember, I want the voltage here. So now I'm going to have, this is going to be in the center right here. Now what I'm going to do is put Z naught over 2 for R, right? So I just put Z naught over 6 because the characteristic, the value of R was Z naught over 3, correct, class? So I'm dividing that by 2, it would be Z naught over 6. Y'all see that? And then I'm going to have just Z naught over 2 here. And this is the value I want for the output voltage. I'll call it, this is V2 here, right? The V out. Y'all follow me? We're assuming it's matched, so there's no problem. All right, well, how do I get that voltage? Y'all see it's simple voltage division. So when I look at V2 over V naught, right? It's going to be this value, so it's Z naught over 2 over the sum of all that, which is Z naught, well, put it this way. It's going to be Z naught over 3 plus Z naught over 6 plus Z naught over 2, right? Now, what do you see happening? Well, I'm going to get rid of the Z naughts, so then I have 1/2 over. Down here, I have a common denominator of 6, so I have Z naught over 3 would be 2. I'll forget about Z naught, so that's 2 plus 1 plus 3, or I'm going to have 1/2 divided, so that's divided by 6, so it's 1/2. Do y'all see that? Now what I've done there is, I didn't say this, I excited this put a voltage here, V naught. This is port 1, right? And remember, if we want S21, that's V2 minus over V1 plus, assuming V2 plus is 0, isn't it? Right? It's the output voltage. This is the forward voltage gain, V2 or S21. So it's V2 minus, this is port 2, so this is what the minus voltage represents here. This would be the output voltage. I excited port 1 with V naught, and I see that I get my output would be, V2 would be V naught times 1/2, or S21 is 1/2. Y'all see that? Right? Now what is going to be, so I'll just put this down there. I have first S11 is equal to S22 is equal to S33 is equal to 0. The reflection, y'all see how that's a symmetric matrix or a symmetric 3-port system, I guess would be the best way. So it doesn't matter how I look at it. I can look down port 1, 2, or 3. It looks the same every way. Z naught is the characteristic impedance. So when I do that, I can see that S11, the reflection coefficient of port 1 was designed to be 0, right? Or this input impedance was Z naught. So I can see S22 and S33. Those are the reflection coefficients are all 0. Correct, class? Right? Now, I just calculated S21 as 1/2, right? Right? Now think about it. What else can I tell you from that? That was the voltage of V naught here, and because of symmetric arguments, I can say that the output on port 3 would also be 1/2 V naught. Y'all agree with that? So that means what? S31, which would be V3 minus over V1 plus, assuming that V3 plus is 0, this would also be 1/2. Y'all would think, I may not like S notation, but that's just, S is just another word for gain. It's the gain from an input on port 1 to an output on port 3. And unless you have an amplifier, it's always 1 or less than 1. Now, unless you have a wacky thing where you don't have the same characteristic impedance, or you do something wacky like I do with just inductors and capacitors, then you can get more voltage out. but you can never get more power up, remember that, unless you have an amplifier. So that's 1/2. So we've got what? We've got all the diagonals. We've got S31. We've got S21. What else can you get by symmetry? Just think about it. What if I excite port 2? Do you all agree out of port 1 and port 3, we get 1/2, right? You agree with me?
Mhm.
So what does that tell you? We can kind of fill this matrix in by symmetry. I think he does this. I don't know if he actually does, but if you look at, for the 3-port divider on page 570, he just puts the 1/2 out in front, and then he goes ahead and fills the matrix. Let's go ahead and do that. I can talk my way through this, but I think, and I don't ask people to do anything too crazy, except to understand basics. So that means the S parameter matrix for the splitter, and I'm starting with the splitter right here. Do you all agree it's going to have a 1/2 everywhere that we use?
Oh.
So I pull a 1/2 out of there. Now, what do I know for sure? I know the diagonals are 0. Start there. All the diagonal terms are 0, right? No reflection. Diagonal terms are just reflection coefficients of port 1, 2, and 3. You with me? All right, what did I calculate? I calculated S21 as 1. That's right here, isn't it?
Mhm.
What else did I calculate? S31 is 1, right? Down here. Now, what else did I calculate without really calculating? I said if I energize port 2, right? Then out of port 3, so I had S what? S32 as 1, didn't I?
Mhm.
Where's S32? Here, 1. That's 1, right? That's 1, and that's 1, I believe. You check me on that. All those are going to be 1. I think that's consistent with his. Yeah. Basically, all the diagonals are 0. Everything else 1. And that's the way a resistor divider will be if it's symmetric. Now that's a good 3-port thing to start with. But most of the time I don't even bother with that because it's useful because it's cheap. But the problem is you're losing a lot of signal right there. You'd never use this on something where you're trying to optimize power, or you might say minimize power loss. And that means in everything that has to do with transmission or reception of a signal, you wouldn't use this. Now, when you're dealing with cable, you got to understand something. The internet stuff that runs to your house, it's coming out of a cable. Basically, they can put as many preamplifiers as they want on the line. It's not a problem, and they're cheap. So when it comes to your house, if you use a splitter or 2, that signal is already very high, and it has to be demodulated. And it's what it is, it's a modulated signal, but it's FM. It's either 1s or 0s. So it's FM, but it is 1s and 0s. They demodulate it, then they take it down and extract the 1s, 0s, the binary stream. And the binary stream at that point, from that point it's on, it's all digital signal processing, there's no noise. If there's one thing really good about digital signal processing, there is no noise. There's, I say that, and somebody's going to yell at me. There is a thing where you do have noise associated with quantization. In other words, it's distorted in some way. Quantization is when you have only so many levels of signal allowable to assign to any analog signal. And there's also something called a sampling error, but it's not a true error. It means you have the highest frequency of interest that can be actually replicated in the output. Do you remember that's twice the highest frequency, twice the highest sampling frequency is the maximum possible frequency that you can replicate without any kind of quote noise. Those aren't true noise. Noise to me is like you run a drill or something like this and you got an AM radio in your or a hair dryer. That to me is true noise. When you get quantization and sampling error noise, what that is most of the times you oversample a signal at least by a factor of 2 anyway. For audio, I mean, you guys know how high you can hear? about 20,000 hertz, all right? And that's you guys, if you haven't been around guns. I've been around guns and I'm old. So if I get over 10,000, it's a miracle, really. Just listen with a 10,000 hertz pitch, you'll see what I mean. Most of the stuff is down around 2,000 to 3,000 hertz that I care about, even less than that. Now, for high fidelity sound, what they do is they'll sample a signal. This is audio, by the way. They'll sample a signal about 40,000 hertz, or a rate 1 every 40,000th of a second. And then, as far as the quantization levels, that's where they get into the dynamic range. If you're talking about an orchestra or performance at Carnegie Hall or something where they have a huge range and depth and there's echoes off the thing, then they'll want to sample the signal. Because remember, it's not just the amplitude, it's also the frequency or how fast the signal's changing. So they may need a dynamic range of 60 dB. That's enormous. They won't sample at 1020, there won't be 1024 levels. There may be like over 4,000, what is it, 4,096? It could be like, instead of 2 to the 9th, 10th, or 11th, maybe 2 to the 16th levels. That's an enormous amount. That means every time you sample, you have 16 bits of data that you have to store, and you have to transmit that at least every 40,000th of a second. You have to somehow modulate it and get it sent. So I'm just telling you some of the things to think about whenever you think about signal processing, what's really going on, and receiving the signal. Now, I'm saying that because all of a sudden, with that level of dynamic range and all that, now we're getting into something where bandwidth becomes an issue, because the amount of information you can send over a channel has to do with the bandwidth. I don't know, you've had comm? You're in it now? Do you Tugnate? Has anybody had Tugnate? Information theory is based on what's called the channel bandwidth, and how much information you can send. You'd be surprised how interesting this is. Shannon Bard, there are people that came up with the information theory of Shannon, I think, up at MIT. Unbelievable amount of interest in this right now for a lot of reasons. But so that's when you don't want signal. That's when you never want to do something like this, right? Because that signal loss will be significant and it will cause a problem. And I'll leave it at that for now. I don't think I did justice to that topic, but I try to do it right there. So the next type of divider, I'm going to do the Wilkinsons next, then I'll do the circulator, because I want to do the 3 ports sort of in a way. This makes sense to you. This is okay, right? It's not bad, but you lose power. By the way, can anybody just estimate on the top of your head how much power you're going to lose? Well, how much power are you going to put in there? If you put in a voltage, say 1, you get a power of V squared, right? Y'all with me on this? Assume Z naught's 1. What do you get out? Well, you get a voltage output of port 2 of 1/2, right? Square that, you get 1/4, don't you? Mm-hmm. What do you get out of port 3? 1/2, right? Square that, you get 1/4. 1/4 and 1/4 is 1/2. You lost half the power. Y'all follow me on that? And that divider, now that's horrible. You lose half the power there, split it again. Next thing you know, you got nothing. I don't know if you've ever tried to split a cable. I don't know if you hire somebody to do this. Anytime I get cable run into my house, I don't pay for multiple TVs. I have them. I'll put splitters in and just do it myself, right? I think most of you probably would too. But you can't split. It used to be chartered in Spectrum. You can't split that more than about 2 or 3 times before you can't decode that signal off a box. I don't know if anybody's tried that, but remember, every time you do that with resistive dividers, you lose power, remember. So the next best thing is something that's lossless, and that's a Wilkinson divider. But still, when you have that, the power in, only half the power is routed to each device, right? Or the power available. So this is a Wilkinson divider. It's IN. All right, with a Wilkinson's divider, this is back in the 60s, so this isn't that old, really. You take a characteristic transmission line of Z naught. This is an interesting one. By the way, this is not a symmetric device. If this is port 1, this is primarily used for splitting signal power, losslessly. And it's also something that is only designed at one frequency. It's got a very small bandwidth. So then what they're going to do is have a transmission line going this way, and a transmission line going this way. These transmission lines will be a quarter wavelength long. This is interesting. And this is going to have characteristic impedance Z naught, characteristic impedance Z naught. Call that port 2, port 3, and this is port 1. Now they're a quarter wavelength long, but the characteristic impedance on these is going to be the square root of 2 Z naught. Y'all see that? Now, between these two, this is the interesting thing. There is a resistor tied that has a value of 2 Z naught. Don't let this scare you. And here's the deal with this. This is in its book. It's on page 571 in my book. I don't know about yours. Now, here's the thing with this one. I think he shows us. Yeah, he does have the parameters. This is one of those, this is interesting. The way it's analyzed is this. And I'm going to tell you, the key for all these things is there can't be any reflection. Now, I'm going to say one other thing. You see how there's a transmission line between here and there? It's losses. Transmission line between port 1 and port 2, losses, right? Here's the resistor, right? But here's the thing about that resistor. Suppose I got a signal. Just listen to me now as I'm talking and think about it. Got a signal on port 1 moving through here, right? Going this way and this way. You all see how the voltage here will be identical to the voltage here because they're in parallel. Mm-hmm. And because of that, the voltage at the top of this port 2, top of port 3 is the same. There's no current that flows through that resistor. That's the key thing. Another good question is, why is it there? We'll get to that in a second. It really doesn't serve a purpose. It does and it doesn't. And I don't have a really good answer for some of these things, but I know it has to do with a balancing effect that happens if there's a phase problem. And I believe that's it, but I'm going to go through the analysis. All right, we don't have to put that resistor in there, that 2 Z naught. So the way they normally do it is this way. They say, and they make the argument, well, the signal is going to split, and this resistor has no current. And the good question is, so why is it there? I'll look into that more. They don't really need to know that. That's not something they worry about. So what they do is look, and they say, well, what if we actually put a signal here? This is kind of a crazy way to do it. Suppose I put a signal V naught here, and I want to analyze this. I don't like this way, by the way, but this is the way they do it. You don't have to do it this way. You could start from this port and just say, well, if this is a characteristic impedance of Z naught, I can find the input. Matter of fact, we could do it that way. If we're at port 1, we want to prove the reflection coefficient is there. We can get the splitter parameters in a second. But at port 1, if we look this way and we want Z in, do you all see that that is the same as this and they're in parallel? Agree? So if I can calculate the input impedance of this one looking that way, and forget about this, just call this Z naught is really going to be what it's terminated into. Just call this Z naught here. and Z naught here, which means it's matched. In other words, this is going to be Z naught, that's Z naught. So that means that Z naught is the load here. This would be Z naught. Y'all follow me on that? And if you look at this, if we just take a look at the transmission line, if I have a transmission line like this, with the square root of 2, Z naught is the characteristic impedance, and the load being Z naught, and this is a quarter wavelength here, and I wanted the input impedance here. All right, I don't know if you remember what Zn is of a transmission line, but Zn of a transmission line is this. You start with the characteristic impedance of the transmission line. It's really Z naught times the quantity ZL plus J Z naught tangent of beta L over ZL plus J Z naught tangent of beta L. I can put that down right here, then I'll show you I'm going to adapt it. So in general, Zn is equal to Z naught, right? Then it's times Z load plus, this is lossless, Z naught times the tangent of beta L over Z naught plus J ZL tangent of beta L. Y'all agree with that? Now I'm going to make this statement. I've already said it's a quarter wavelength long, right? So if L is equal to lambda over 4, beta times L is 2 pi over lambda times lambda over 4, or it's pi over 2. Agreed?
Yeah.
You agree with that? Let me make sure. Now, what is the tangent of pi over 2? Tangent of 90 degrees. Going to infinity, right? You agree? It's headed to infinity. So if I look at this, when beta L, tangent of beta L, is going to infinity, the first two terms are insignificant. Do y'all agree with that? And that means my Zn, and I'll put it right here, if L is equal to lambda over 4, would be equal to Z naught squared over ZL. You agree with that? Okay. Now, based on that, look over here. So my actual transmission line impedance is square root of 2 Z naught, right? When I square that, I get what? 2 times Z naught squared over ZL, which is Z naught. Or it's 2 Z naught. Do you all agree with that? Can you see it, honey? All right. So that's the impedance of one of these transmission lines looking this way, right? What's parallel impedance to the two? Z naught, isn't it? Mm-hmm. Isn't that the impedance we're coming from? Huh? Therefore, the reflection coefficient is 0. Now, all right? 2 Z naught in parallel with 2 Z naught is what? Right? Because that's 2 Z naught is the input to this one looking this way. This is 2 Z naught there in parallel. Characteristic impedance would be Z naught, and therefore the reflection coefficient is 0. Do y'all follow me? So the minute you check that box, I see it's nothing but coax cables. I know it's lossless. I know I'm going to get what I want out of here, which means the output over there is going to be the square root of 2. Output here is square root of 2. Now, how do I know that? Because when I square those outputs, assuming the characteristic impedance is 1 and the input voltage is 1, I put 1 in, the power would be V squared would be 1. The output, if it's square root of 2, 1 over square root of 2, is going to be 1 over square root of 2 squared is 1/2. On this port, it would be 1/2, 1/2, 1 plus 1/2 is 1. Same power in equal power out. Y'all follow me? Now on this one, there's an interesting thing that happens here. This is a quarter wavelength long. I'm not going to get into this too much. Y'all follow me? When we talk about a quarter wavelength, we really talk about a phase change of 90 degrees, don't we? If it was a full wavelength, it would be 180, or excuse me, 360 degrees. Quarter wavelength is 90 degrees, or it's e to the j pi over 2, or just j, right? J is 90 degrees, isn't it? And if you look at the scattering parameters of this is an interesting one. So if I look at the scattering parameters, now I want you to see this. There is no, if I looked at S32, well, just look at this. That signal can't get out here. That's 0. And S23 is also 0. Now, some of you will say, oh, I'm not sure. I can actually go ahead and prove this to you. And the reason it is because if you look at this right here, I think that resistor always takes a role on this thing. For this thing to get here, there is no direct path, is it? It has to go this way. Well, by the time it hits this point right here, and we can go through that, when it hits this point, there is no, it can't get back this way. So I'm going to look at that because this one will take a little more time. I can actually do it if you have time, but when I look at this for the S parameters, the Wilkinson, he doesn't do it in his book, but you'll see a J over the square root of 2 out in front. And then what he's going to have on the diagonal, all zeros, right? And then when I look at S21, it's 1, and S31, it's 1, right? And then I think he's got port 1 being that. Yeah, he's got that right. Then these two are 1 as well. And these two are 0. These are S23, S32, and that's S33. But these are 0 because there is no coupling between them. Here's how they actually do this thing. They put a voltage here, and then what they're going to do is analyze it back this way. By the way, I think that's exactly where that 2Z0 comes in, because what it'll do is cause the signal from any backflow this way. Take me a little while to prove that, and that'll be the scattering parameters for the Wilkinson divider. Now, that said, Wilkinson's divider are really power splitters or losses. That's all they are. Signal comes in here, it splits evenly here and here. That's the bottom line. Exactly half the power goes that way, half the power that way. They're not used for any other purpose that I know of. They don't have to worry about power coming back here and going out port 1 or power coming back here. The real benefit of a Wilkinson divider is 0 power loss. The downside is this. It only works at 1 frequency because this is physically fixed at a length L. At different frequencies, it changes. It's no longer a quarter wavelength. Follow me? So Wilkinson's dividers have narrow bandwidths. In anything that's wideband, we get more than like about a 5% change in the center frequency. These things start failing. Fair enough? Okay. Next is a circulator. With radar, a circulator is primarily used for the transmit-receive signal. And a good question that probably most of you have, some of you have at least, is how do you make a circulator? And the truth is this. They use they're going to use either one of two things. Either they're going to have materials that are sensitive, or they're magnetic materials, or they're going to use, I mean, you know how diodes are nonlinear and stuff like this? All right, they will have something with diodes. By the way, I don't think he shows you anything about circulators, but circulators, generally speaking, I can't say this with absolute authority, but they have magnetic fields that actually cause the circuit, or cause the signal to route in different directions. And I wish I had an example of one. I don't think he shows. He shows you a picture of a circulator. Well, he does say a typical circulator is layered. It is layered construct consisting of discs of ferrite and permanent magnets. So he does talk about it. This is on page 568. If I can get a picture, I want to show you. Circulators are kind of interesting, but you got to understand something that magnetic materials really have, it's kind of interesting the way this works. If you think about this, you know how, you know what the Lorentz force is, how if you have a charge moving in a magnetic field, it experiences a force QV cross B, and it bends in a certain way, right? Well, when you actually have magnetic materials and you induce currents, and you do, what will happen is if you have magnetic fields, the currents are induced to flow in certain directions, and you can bend the actual wave as it propagates one way or the other based on the magnetic field. I'll say one other thing, because the materials, you do have slight loss. You don't get perfect losses. And I guess you don't get that either in a transmission line per se. All real materials have some loss. But anyway, the circulator, this is the deal. Port 1, port 2, and port 3. I was showing you this last time. The deal is this: anything in port 1, and it doesn't have to be this route, they want coming out port 2. Anything coming into port 2, they want going out port 3. So that's the idea. In any kind of thing coming in port 3, this is what he's going to show you, they want out port 1. So this would be the direction, the arrow direction. Now, honestly, in the truth, they don't care about this 99% of the time. Here's what usually happens with these that I know. They'll have an antenna here. This is at least for radar work. So this is going to hook to some antenna that's going to be transmitting or receiving. Over here, you're going to have a power amplifier putting signal in. And remember, I showed you the radar waveform. They're on, they're off, they're on, they're off, on and off, right? So it's on, it's off, it's on, it's off. When signal goes out and comes back, it comes in, it can't go this way. There's no coupling path. It has to go this way. This will be the signal processing or demodulation. That's usually the way a circulator works. Anything going into this port goes out that port. Anything coming into this port gets routed this way. That's just the way it is. That's really what they want. Now, in his book, he says, well, a true circulator would route something, anything coming in here would go that way. The fact is there's never anything coming in there from radar. All right, but a true circulator only takes information in a port and moves it to an adjacent port. Anything coming in this port goes out the next port. In this port, out the next port. In this port, out the next port. That's a true circulator. And they are built with magnetic materials. And I might add that I have not torn one of these apart, but I think they're fairly expensive. This is not cheap, in other words. There's another way to do this with radar. It's very fast switches where you actually have an electronic switch that becomes a short, and then it's an open, and another part gets shorted. Like a transmit, this is a short, this is an open. Then when I want to listen, this is going to be an open, this is a short. You follow me? It's a toggled switch. And they do that with FETs, but circulators are used a lot for very high-speed stuff, I can tell you that. Okay, so what are the scattering or the transmission parameters? Well, the first thing, this is a 3-port. So for a circulator, all right, all the reflection coefficients, S11, S22, S33 are 0. They should be. There's no reflection coefficients. If there are reflection coefficients, you got a problem. I don't know if he shows you. Does he show you a circulator? Yeah, he does. On 1036, he does. Now, here's how you get the rest of it. You all understand this is S11, S22, S33. Anything other than 0, they may not be exactly 0, but they're very small. Anything other than that, and you lose a lot of power. So, and you got crap. I mean, you saw that one where you had a half, that's bad. You're losing half the power in a resistive divider. Now, remember, we wanted what? We wanted V2 minus over V1 plus to be equal to 1, right? That's S21, correct? Well, S21 is right here, right? Now think about it. Then anything into port 2 coming out port 3, so we have S32 is 1 also, right? Because that would be what? That would be V3 minus over V2 plus, assuming it's matched everywhere. Correct, class? We want that to be 1. And where's S32? That would be here, right? Correct? Now, what else do we want 1? Well, really, we want what? S13, right? We want S1. This is going to be S13, or it's really V1 minus over V3 plus. It's coming in, so it's V3 plus, that's port 3. Coming out V1 minus, we want that to be 1. So that's S13, that's here. And all the rest are going to be 0, right? That's exactly right. And if you look in there, that's what he has in equation 1036. Y'all see that? On page 568 in my book. All right. Remember, the way I'm doing this, I'm just trying to show you, get the diagonals at 0. If it's a circulator, or if it's any kind of a splitter, has to be. Because if you get a reflection coefficient, it's not 0. The whole thing's, I mean, we don't, in a sense, in some cases, exactly 0, but it's very close. Or else you're getting, you got nothing really coming out. So that's 3-port. Now in 4-port, we can go to N-port. But 4-port, what this book talks about, the thing about it is, he says the 4th port really is just grounded. It's not used for anything. Here's the one thing I'm going to tell you. A lot of times what happens, whenever you're taking, you got 4-port devices, you're going to have signal coming in port 1. Some of that signal's routed out port 2. Then maybe a smaller amount, maybe only a third of the power goes out port 3. And then port 4 is going to have just a little bit of the signal left, and that's for synchronization. That's for the internals, right? Not to be sent. But 4-port devices are typically, well, they've got them out there, but he just mentions it probably because he used one at some point in his life. They're not that common. I mean, at least I can't think of anything. Circulators are, the Wilkinson's dividers are. And to be frank about it, how would you make something divided power 3 ways evenly? What would you want? Think about the Wilkinson. What did I do with a Wilkinson divider? I had transmission lines, right? And I had the input impedance of the first transmission line such that when it was parallel with the second, it would have a characteristic impedance of Z0, right? What if you had 3 ports? You wanted to take power and split it 3 ways. Well, then you would have the input impedance not to be 2 Z0, but 3 Z0. You follow me for just one? And then if you had 3 in parallel, it would still be Z0. And that's how, in general, you make as many ports as you want have equal power. Now, in general, yeah, I mean, you guys never worry about circulator design. The reason is it's well out of the scope of this class. In most of it's using magnetic materials. That's not even electrical engineering. That's really materials science or materials engineering. If we're doing it with FETs and stuff like that, then it's fast switching. We can do that. That would be in the microwave class probably. I think Stu teaches that. If you get a doctoral level course, it might be Mike Hamilton or Mark Adams. I haven't taught that, but I would like to. And I can only tell you one thing. The big thing about this whole deal with 2-port, 3-port, 4-port, or N-port is just understanding the concept. There's 1 of 2 things that are going to happen. Either I'm going to take a signal, a power signal, and divide it up in ways, or I've got signal and I want any signal coming in, going out 1 port, and anything coming in that port that the signal goes out to go out another port. That's really the bottom line in all this stuff. There's nothing more to it. We can talk about S parameters till we're blue in the face, but that's it. All right. Now, I'm going to make mention of one other thing. He talks about insertion loss, and he'll talk about return loss and all this stuff. Do y'all remember when we talked about shielding? We talked about shielding effectiveness, right? And the only thing we did was if it's a voltage, we take 20 times the log output versus input, right, for shielding effectiveness. And if it was a power, it was 10 times the log of the output power, input power, right? Well, with insertion loss or return loss, insertion loss always boils down to the parameters like S21, the input-output relationships. You still have 20 times the log of the S parameter. I'll put it up there. Y'all with me? It'll be, because the S parameters are voltage, not power related. And if it's reflection loss, it's going to be the S11, S22, S33 parameters. And I'll put this down here. But it's really just to put everything in terms of dB. There's nothing fancy about this because most of the time when you deal with S parameters, like you get this. I shouldn't say most of the time. Many times. When we talk about anything that is inserted in a circuit, so if this is port 1 and this is port 2, and we have a 2-port system like so. All right. Then I'm going to have S parameters where I'm going to have S11, S22, S21, and S12 here. And when I look at this, if I talk about return loss, it's RL, which is return loss. It's equal to minus 20 times the log base 10 of the magnitude of S11 if you talk about port 1. If you talked about port 2, this would be port 1, it would be minus 20 times the log of the magnitude of S22. You can see that that's just a reflection coefficient. So it's just like the return loss on a transmission line of dB. With me? Now, if the return, and it should be what? If S11 is 0, right? Where does that head it to? Log of 0 is minus infinity. It's going to infinity, isn't it? Right? Now, then you talk about the insertion loss. And this is insertion loss. And that's equal to minus 20 times the log. And for this, S21 would be the insertion loss between a signal coming in port 1 going out port 2. So it would be insertion loss, and this would be something like IL, and he would have 2-1. And it could be IL12, which would be the reverse voltage gain, minus 20 times the log of the magnitude of S12. And he should put this in his book. And he does. On page 573. But he talks about coupling, and he talks about other stuff. But the real thing is this. Anytime you get loss, return loss will either be 1-1, 2-2, 3-3, because it's a reflection. Insertion will either be 2-1, 3-1, maybe 1-2, 1-3. It'll have that. But the designation of the first subscripts right here, 2-1, 3-1, 7. That just means you take minus 20 times the log of the magnitude of that S parameter. That's all it means. There's nothing else to it. Do you all follow me? And he uses the term coupling in there and stuff like this. You don't have to worry about it. It's not used. Most of the time, what they'll do is they'll have something like they'll have, for the insertion loss, it'll be between port 3-1 and port 4-1. So it'll be the output coming out port 4, which is the coupling port. And it'll be like 50, 60 dB. But you don't have to worry that much about it. Now, what am I going to test you on? With your understanding of couplers, I'll give you some problems. But basically, if I drew a simple circuit, where instead of, if I have really, here's what it boils down to. You all know how to get S parameters for 2-port, right? I put an inductor, a capacitor, a resistor in a very evil way last time and made you have fits over your calculators, right? I'm not going to do that for 3-port. It gets too crazy. But if I said it's a power divider, a 3-port, and I put something, you know the principle of everything in parallel, just take the value of one portion divided by the number of ports. Something like that would be reasonable. I'll give you some problems on this, all right? Here's what I'd like to do. I got 9 minutes. For the final exam on Friday, here's what I'd like you to do. Look at the stuff that's available. If you got questions, ask me. I mean, we started in chapter 6. We ended through 10, right? We did antennas, we did radar, we did freeze, right? We did reflection, we did shielding, we did waveguides. Now we've done S parameters. We didn't build amplifiers. When we're testing things on amplifiers, we can do that. I don't like doing it here because, frankly, you basically don't have time to do anything real. I think you do that in a microwave course, or I think you get high-frequency design courses if you want them. It's an elective. I recommended Foster Dye, Dr. Dye. Teaches something. Have you had him? You had him for analog.
Yeah.
Well, if you can get him for high frequency, because his work has been in radar, you get him for high frequency circuit design or anything like that, take him. I think he'd benefit. I do radar in the spring. I guess you guys are, I don't know if you're going to be here. Some of you are co-oping, right? So in the spring, if you're interested in radar, the radar course is a lot of fun. It's applicable to the drone technology and a lot of stuff going on where they try to not just have an amplifier for radar, but they try to use radar and comm. I try to do this. It's integrated into one system. So when you transmit, you don't just transmit a signal to see the reflection. You also got communication information. So other people in the area can hear you, and that means only one system really can be used for communication and radar, which is this is what they're trying with drone technology and a lot of stuff. think I mentioned package deliveries, a lot of stuff is gonna happen. We literally, and it's in major cities, I'm told, in San Francisco, places like this, they literally have like a teleport for your delivery of packages up to so much in weight. And they'll have one of these drones fly in and just drop it off. Has anybody seen this? You should look this up, because this is what's happening. The next 5 years, man, you're going to have autonomous vehicles all over the place. You may not even have to drive to work. You'll get in your car, per se, and it will drive you to work. Teslas do that now, I think. And there's a Google car out. So I don't really know how fast it's going to evolve, but I have a feeling it's going to evolve very fast in major cities. That's my take on it. The problem is non-compliant vehicles, because your eyes can tell when an idiot's up there, and the car can't. And that's the one thing that you want a manual override always. And so when you're on the highway working with some guys dropping, dynamite off a bridge half-mile down, you can stop. Tesla won't, but you can stop. And that kind of stuff is always what they worry about, is non-compliant or people with malice that are trying to destroy you. But that's what you guys are going to, your world is going to be a world of autonomous vehicles, robotics. You hear about Siri, right? Your home, what is it? You can have your home basically wired so if you want basically lights out, you can put lights out. If you want to change the temperature, you can change it on your phone. I'm not lying about this. This is absolutely available to you right now if you want. You can control everything from your remote. My wife's got cameras in the house. Nobody comes to our door without her knowing. She's got a camera in the main living room. She watches our dog. Can tell us when if the dog decides to tear something up, she'll know about it. The dog can't get away with anything. She sees when I'm doing something I shouldn't be, like eating the refrigerator. Yeah. But I mean, this is going to be the world you live in. I'll tell you one other thing. This is my own personal advice to you guys. If you ever get a chance to take anything with artificial intelligence, machine learning, neural nets, please do. That's going to be the mainstay of a lot of decision making and design. I use genetic algorithms. I use computers to do a lot of design already. AI takes it to a step. Do you understand the fundamentals of this? You know how you teach a dog to do certain stuff, right? It's repetitive tasks where you give rewards and punishments. Well, with AI, you have things called neurons. It's not really, I don't even know what they call them. What you do is you say, you see this is good. So it has a figure of merit. That's good. That's what I want. This is bad. And it's an electronic binary decision-making thing. And you teach these out. It's amazing. And that thing is what I'm looking at using the AI to do this for radar, teaching radars how to distinguish targets from non-targets based on very, you might say, raw signals that otherwise you have to process the crap out. But there's ways of doing this. Anyway, I'm very interested in that. That's my advice to you. And the one other thing I'd tell you is, at this point in your career, take a look downfield what you want to do in 5-10 years, and then make a plan to do it. Because there's one thing about this: if you're trying to achieve nothing, you'll do that. If you got no goal in life, you'll do that. But I would encourage everybody to consider graduate school. You'll never regret an advanced education. But somewhere down the line, you'll regret you didn't do it if you have the opportunity to. And most of you guys, I think this is a good class. Overall, I'd say that I'd encourage all of you to think about graduate school is paid for, by the way. You don't pay for it. If you are, are you guys Chinese nationals still or not? If you are, I don't think China pays for it. I don't know. No?
Pay for what? For
graduate school, nobody pays for it if you're an engineer. You can.
I think it's only it's only a little bit of the people.
All right, well, let me just cut to the chase, all right? If you're a graduate student from a foreign country and you go here, your major professor pays you to do research, and graduate school is free. All right. and you have to be accepted. If you're an American citizen, you can apply for fellowships if you have a high GPA. They pay at the rate of $30,000 to $40,000 a year. There's national fellowships, and all my American grad students, except for one, I think, maybe two, didn't have a fellowship from a national, from the federal government. Or a professor can pay you, but preferably you get a fellowship because it's nice. You don't have to write reports or anything. For 3 years, you get to do what you want to do, and then you graduate your PhD. Or you can work for somebody as a graduate student, basically doing research projects and publishing and stuff like this. But you'll never regret grad school. And I don't think anybody really tells you how important it is. So please consider it. There's National Science Foundation, NSF fellowships. There's Department of Defense, DOD fellowships. There's SMART fellowships. There's NASA fellowships. All these, one of my students have had in the past. Some have had multiple. There's all these private fellowships. Auburn University has a presidential fellowship that I think my grad students are going to get now. This is a grad student who hopped in late, and he's an American. In other words, there's so much opportunity, and you'll never regret it. Here's what you regret. 10 years down the road when you got 2 kids, and you think, boy, I wish I had advanced degrees, because there's opportunities all over for people with advanced degrees. There really are. It's hard to come back. Regardless of what people say, I'll tell you one thing, my master's professor, I thank him to this day for this. His name was Stack, and he said, get the last degree you're going to get sequentially. Don't take a year off, because all that information you got right now, you're going to use.